There's something undeniably intoxicating about staring up at the night sky, about that fleeting sense of wonder when you realize just how much lies beyond what our eyes can see. We've mapped continents, scaled mountains, and plunged into ocean trenches, yet the universe still guards its most profound secrets with absolute defiance. Beyond the familiar glow of stars and planets, there exist places so bizarre, so utterly alien, that they might as well be from another dimension. Regions where the laws of physics twist into knots, where time and space behave in ways that defy logic, and where the very fabric of reality seems to unravel. These are the cosmic frontiers that remain forever out of reach, no matter how advanced our technology becomes. Think about that for a moment. In a universe spanning tens of billions of light years, filled with trillions of galaxies, there are pockets of existence so hostile or mysterious that we may never set foot or even gaze upon them. Some are too distant, hidden behind the impenetrable curtain of expanding space. Others are so extreme that any probe or signal we send would be instantly obliterated. And then there are those that challenge our very understanding of existence, places where matter behaves unlike anything we've ever witnessed. These enigmatic regions aren't just unexplored, they're fundamentally unexplorable, at least for now. But that doesn't mean we can't try to understand them. Today, we're embarking on a journey to the edges of the known cosmos, to 25 of the most perplexing, awe-inspiring, and downright terrifying places in the universe. From the crushing depths of black holes to the eerie voids where galaxies refuse to form, each of these realms holds clues to the grandest mysteries of existence, and each one reminds us just how small, yet how curious we truly are. So if you've ever wondered what lies beyond the limits of human exploration, beyond even the reach of our imagination, you're about to get closer than ever before. Buckle up, the universe has secrets it's not eager to share, but we're going after them anyway. The universe has a way of humbling us with its sheer scale, but few things are quite as unnerving as realizing we're being pulled towards something we can't even see. Hidden behind the thick curtain of stars, gas, and dust in our own Milky Way lies one of the most perplexing mysteries in modern astronomy, the Great Attractor. This colossal gravitational anomaly, roughly 250 million light-years away, exerts an irresistible pull on our galaxy and thousands of others, dragging them toward an unseen point in space like some cosmic puppet master. Yet despite its overwhelming influence, we know shockingly little about it. The Milky Way's dusty disk blocks our view, leaving astronomers to piece together clues like detectives working with half-erased evidence. What makes this region even more baffling is how it defies expectations. Based on the visible matter we've mapped, the Great Attractor shouldn't have enough mass to generate such a powerful gravitational tug. That means either there's an enormous amount of hidden matter, perhaps exotic dark matter lurking there, or our understanding of gravity itself is incomplete. Some theories suggest it might be the heart of a supercluster we've yet to fully map, while others speculate it could be a gateway to something even larger, a vast cosmic structure we can't yet comprehend. Efforts to peer through the so-called zone of avoidance, the obscured region of space where the Great Attractor resides, have relied on infrared and radio telescopes, tools that cut through the dust like cosmic X-rays. These observations hint at an unusually dense concentration of galaxies, but the full picture remains frustratingly blurry. It's as if we're standing outside a locked room, hearing whispers of movement inside but unable to open the door. And with the expansion of the universe accelerating, this mysterious region is being carried away from us faster than we can study it. One day, it may vanish beyond the horizon of observation forever, leaving its secrets forever out of reach. The Great Attractor isn't just a scientific curiosity, it's a reminder of how much lies beyond our line of sight, how the cosmos guards its mysteries with quiet defiance. Every galaxy caught in its pull, including our own, is part of a slow-motion migration we're only beginning to understand. what awaits us in that distant, shadowed corner of space. For now, the universe isn't telling. If the Great Attractor feels like a cosmic force pulling us toward the unknown, the Boötes void is its polar opposite, a staggering expanse of almost nothing at all. Stretching an incomprehensible 330 million light-years across, this region of space is so desolate that astronomers have nicknamed it the Great Nothing. Picture a sphere so vast you could drop our entire Milky Way galaxy into it 60 times over, only to watch it drift through a near-perfect vacuum, isolated from neighbors by distances that defy human intuition. What makes the Boötes void so unsettling isn't just its size, it's the eerie absence where there should be abundance. In a universe teeming with galaxies, where even the darkest corners host at least a few celestial objects, this void contains fewer than 60 galaxies. To put that into perspective, a typical region of space this size would hold thousands. It's as if someone carved out a sphere of the cosmos and left behind only a handful of scattered stars, like lone survivors in an endless desert. Theories about how such a void could form range from the plausible to the mind-bending. One leading explanation suggests it's the result of smaller voids merging over billions of years, like soap bubbles coalescing into one gigantic emptiness. Another, more radical idea proposes that the Boötes void might be evidence of an ancient collision with a parallel universe, a cosmic bruise left behind by something beyond our reality. But perhaps the most haunting possibility is that the void isn't truly empty at all. Instead, it could be filled with dark matter, an invisible scaffold that gives the universe its structure but refuses to interact with light, leaving us blind to its presence. Even more puzzling is how the void challenges our understanding of galaxy formation. The few galaxies that do exist within it aren't just rare, they're weird. Many are irregular in shape, lacking the elegant spirals or smooth ellipses we're accustomed to, as if the void itself starved them of the material needed to grow properly. Some astronomers speculate these galaxies might be outcasts, flung into the void by gravitational interactions billions of years ago and left to wander in isolation. Others wonder if the void's extreme environment has altered them in ways we don't yet understand. Despite its name, the Boötes void isn't completely empty, and that's what makes it so fascinating. Those sparse galaxies might hold the key to unraveling its mysteries, acting as cosmic breadcrumbs leading us toward answers. Yet for now, the void remains one of the universe's most profound enigmas, a reminder that sometimes the most revealing thing about space isn't what's there, but what isn't. Somewhere beyond the edges of everything we can observe, something immense is pulling at the fabric of our universe with a force we can't ignore. This is dark flow, an eerie, large-scale motion where entire galaxy clusters stream through space at breakneck speeds, all racing toward a point so distant it lies beyond the cosmic horizon. Imagine throwing a handful of leaves into a river and watching them all drift in the same direction, pulled by some unseen current. Now replace those leaves with galaxies, each weighing billions of stars, and the river with the vast emptiness of intergalactic space. That's the scale of the mystery we're dealing with. The discovery of dark flow sent shockwaves through cosmology because it defies our most fundamental understanding of how the universe should behave. According to the standard model, matter should be distributed evenly on the largest scales, with no preferred direction of motion. The expansion of space, driven by dark energy, should be the dominant force shaping how galaxies move. Yet here we are, watching thousands of galaxy clusters, some as distant as 3 billion light-years, all hurtling toward the same patch of nothingness at speeds exceeding 2 million miles per hour. It's as if the universe itself has a hidden tilt, a slope we can't see but everything else seems to feel. What could possibly exert such an immense gravitational pull? One controversial theory suggests the culprit might lie outside our observable universe, perhaps a colossal structure in a neighboring region of space-time, something so massive it bends the fabric of reality beyond our cosmic horizon. Picture a mountain looming just beyond the fog. We can't see it, but we can feel its shadow. Some physicists speculate this could even be evidence of a parallel universe, a neighboring bubble in the multiverse exerting gravitational influence on our own. If true, dark flow wouldn't just rewrite our cosmic maps, it would shatter the idea that our universe is all there is. But not everyone is convinced. Skeptics argue dark flow might instead expose gaps in our current models, like flaws in how we measure galaxy movements or imperfections in our understanding of gravity itself. After all, the farther we look into space, the fuzzier our data becomes. Distant galaxy clusters are dim, their motions hard to track with precision. Could this just be a cosmic mirage, a trick of incomplete observation? The debate rages on, with each new study either fueling the mystery or chipping away at it. One thing is certain: dark flow forces us to confront the limits of our knowledge. If it's real, it hints at a universe far stranger and more interconnected than we ever imagined. If it's an illusion, it reveals just how much we still have to learn about the forces shaping existence. Either way, this enigmatic motion reminds us that the cosmos still holds cards it hasn't shown, and we're only beginning to sense the hand we're playing against. Rising like colossal ghosts from the heart of our galaxy, the Fermi bubbles are two vast orbs of high-energy gamma rays, each stretching 25,000 light-years into space, one towering above the Milky Way's disk, the other plunging below it. Discovered just over a decade ago by the Fermi Gamma Ray Space Telescope, these faint but monstrous structures glow with the aftermath of unimaginable violence, their edges sharp as if carved by some cosmic blade. If our eyes could see gamma radiation, the bubbles would dominate the night sky, each spanning a width 50 times greater than the full moon. Yet despite their staggering scale, we're only beginning to unravel what unleashed them. At the center of this mystery lies Sagittarius, a star, the supermassive black hole anchoring our galaxy. One leading theory suggests the bubbles are remnants of a frenzied feast, a time when Sagittarius, a star, devoured an enormous cloud of gas or even a star, belching out jets of energy so powerful they punched through the galactic disk, leaving behind these lingering shockwaves. Computer simulations show such an event could have happened as recently as a few million years ago, a blink in cosmic time, with the black hole's fury inflating the bubbles like balloons made of pure radiation. But not all astronomers are convinced the black hole is solely to blame. An alternative idea points to the galaxy's frenetic past, when vast swarms of massive stars were born and died in rapid succession near the center. Their explosive deaths as supernova could have collectively pumped enough energy into the surrounding gas to create these titanic structures. Imagine thousands of stars detonating in a cosmic chain reaction, their combined force rippling outward to sculpt the bubbles we see today. Then there's the eerie possibility that the Fermi bubbles aren't entirely unique. Similar structures have been spotted in other galaxies, hinting that this might be a universal phase galaxies undergo, a violent adolescence of sorts. What makes ours so intriguing is the way they interact with the Milky Way's halo of dark matter. Some researchers speculate the bubble's gamma rays could be tracing the invisible scaffold of our galaxy, offering an accidental map of the dark matter itself. What's certain is that these enigmatic bubbles are more than just a fossil of past chaos. They're a dynamic laboratory, their gamma rays carrying encrypted messages about the forces shaping galaxies. Every new observation peels back another layer, revealing just how little we understand about the heart of our own cosmic home. One thing's clear: when it comes to the Milky Way center, serenity is only an illusion. We might think of our cosmic neighborhood as just another ordinary patch of the universe, but what if we're actually floating inside a cosmic desert, a vast, underdense bubble that distorts our entire view of reality? Enter the KBC void, a controversial region named after astronomers Keenan, Barger, and Cowie, who first proposed its existence. Unlike the Boötes void's staggering emptiness, this one hits closer to home, literally. At roughly 2 billion light-years wide, it envelops not just the Milky Way but our entire local group of galaxies, positioning us at the heart of a void that's nearly 7 times larger than average. The implications are staggering. If true, it means we've been misjudging the universe's expansion rate, matter density, even the very scale of cosmic structures, all because we've been peering out from inside a cosmic funhouse mirror. What makes the KBC void so contentious isn't just its size, it's the way it challenges our assumptions about homogeneity. According to the cosmological principle, the universe should look roughly the same everywhere on large scales. Yet here we are, seemingly anchored in a pocket of space with far fewer galaxies and galaxy clusters than the dense supercluster walls surrounding it. Picture standing in a valley surrounded by towering mountain ranges. From our vantage point, the terrain might seem flat, but step back and the elevation shifts dramatically. That's the dilemma astronomers face. Is this void real, or is it a statistical fluke in our measurements? Proponents of the KBC void point to peculiar observations. Measurements of Type Ia supernova, the standard candles, used to gauge cosmic distances, appear dimmer than expected if space were uniformly filled with matter, suggesting we're inside an underdense region where expansion accelerates slightly faster. The cosmic microwave background, the afterglow of the Big Bang, also shows subtle temperature dips aligned with the void's proposed location. Even the distribution of nearby galaxies hints at emptiness, with surveys revealing fewer neighbors than models predict. Critics, however, argue these anomalies could stem from overlooked biases. Our telescopes might be missing faint galaxies in the void's outskirts, or local peculiar motions, like the tug of the Great Attractor, could be skewing our data. Some simulations suggest such voids should be rarer than 1 in a million, making our apparent position at the center statistically suspicious. If the void exists, why are we so improbably lucky or unlucky to be here? The stakes couldn't be higher. If the KBC void is real, it could resolve one of cosmology's biggest headaches, the Hubble tension, where conflicting measurements of the universe's expansion rate disagree by a significant margin. An underdense region would mean we've been underestimating how fast space stretches beyond our bubble. But if it's an illusion, the tension might signal something even more profound, a flaw in our understanding of gravity or dark energy. For now, the KBC void remains a ghost in the data, a tantalizing what if that forces us to question not just our place in the cosmos, but the very tools we use to map it. Whether it's a cosmic quirk or a paradigm-shifting truth, one thing is certain. The universe has a knack for reminding us that sometimes the most revealing discoveries begin with realizing we've been looking at the picture all wrong. The cosmic microwave background, the ancient afterglow of the Big Bang, should be nearly uniform, a tapestry of subtle temperature variations whispering secrets of the universe's infancy. But one patch in the constellation Eridanus breaks that rule with chilling defiance. Known as the Cold Spot, this region of space is cooler than its surroundings by a puzzling margin, as if someone carved a cosmic freezer into the fabric of reality. Stretching over 1.5 billion light-years, it's too vast to dismiss as random noise. So what's casting this shadow across the cosmos? One provocative answer points to the Eridanus supervoid, an alleged cavern of emptiness so colossal it might bend the very laws of physics. Voids aren't rare. The universe is littered with pockets where galaxies are scarce, but the Eridanus supervoid, if real, would dwarf them all. Picture a spherical abyss so large it could swallow thousands of Milky Ways whole, its sheer scale warping the space-time around it. Photons from the cosmic microwave background, traveling through this void for billions of years, would lose energy as space expands within it, cooling the light we observe today. It's a phenomenon called the integrated Sachs-Wolf effect, a subtle but measurable fingerprint of cosmic structures on the universe's oldest light, the problem. Simulations suggest a void this size should be vanishingly rare, so rare that some astronomers argue it can't explain the cold spot's extreme chill, that's where things get weird. Alternative theories veer into speculative territory, suggesting the cold spot might be evidence of something far stranger, a cosmic texture. These hypothetical defects in space-time would stem from phase transitions in the early universe, like cracks forming in ice as it freezes. If one of these textures collapsed, it could have released a shock wave of gravity, leaving behind a cold imprint as an echo of its demise. It's a fringe idea, but one that tantalizingly bridges particle physics and cosmology, hinting at forces we've yet to discover. Yet the debate rages on. Skeptics point to flaws in the void hypothesis. Some studies find no significant underdensity of galaxies in the cold spot's direction, while others argue the temperature drop is exaggerated by statistical artifacts. Even the Planck satellite, our most detailed map of the cosmic microwave background, hasn't settled the question, its data simultaneously fueling both sides. The cold spot endures as an enigma, a Rorschach test for cosmologists. Is it a cosmic illusion, a gap in our models, or a window into physics beyond the standard model? What makes this mystery so compelling isn't just the science, it's the philosophical weight behind it. If the cold spot stems from a supervoid, it challenges our understanding of how structures form in the universe. If it's a cosmic texture, it opens doors to new physics, and if it's neither, then we're forced to admit there's a phenomenon out there we haven't even imagined yet. The Eridanus cold spot doesn't just defy explanation, it dares us to rethink the rules. The cosmic microwave background is often called the universe's baby picture, a snapshot of its earliest moments frozen in time. But what if this ancient light held a secret, one that seems to whisper our solar system, holds a privileged place in the cosmos? This is the unsettling mystery known as the axis of evil, a bizarre alignment where the fluctuations in the CMB's temperature appear to sync with the plane of our solar system. It's as if the universe's oldest light is subtly nodding toward Earth, defying everything we thought we knew about our unexceptional place in the cosmos. At the heart of the controversy is the Copernican principle, the bedrock idea that Earth isn't special, that we occupy no favored position in the universe. For centuries, this principle has guided astronomy, from displacing Earth from the center of the solar system to revealing the Milky Way as just one galaxy among billions. Yet the axis of evil throws a wrench into that view. When scientists mapped the CMB's subtle hot and cold spots, they expected randomness, a cosmic fingerprint with no discernible pattern. Instead, they found a peculiar correlation. Many of these fluctuations align eerily with the ecliptic, the plane in which planets orbit the Sun. The odds of this happening by chance? Less than 1 in 1,000. Could this be a fluke, a statistical mirage in the data? Some researchers argue it might stem from overlooked systematic errors, like contamination from foreground dust or quirks in telescope calibration. Others point to the kinematic dipole, a Doppler-like effect caused by our solar system's motion through space, which might imprint a subtle bias on the CMB. But even after accounting for these factors, the alignment persists, gnawing at the edges of cosmological orthodoxy. Then there are the more radical explanations. One hypothesis suggests the axis of evil might be a relic from before the Big Bang, a scar left by an earlier universe that influenced the birth of our own. In certain cyclic cosmology models, our universe is just one in an endless chain of expansions and contractions, each leaving faint traces in the next. If true, the alignment could be a cosmic fossil, a fleeting glimpse beyond the veil of our own existence. Alternatively, some theorists propose the universe isn't uniform on the largest scales at all, that we might live inside a vast, anisotropic bubble where the rules of physics vary subtly from place to place. This would mean the Copernican principle, at least in its strictest form, might need revision. The implications are staggering. If the universe has a preferred direction, even on the grandest scales, it would rewrite textbooks overnight. For now, the axis of evil remains one of cosmology's most persistent anomalies, a riddle wrapped in ancient light. Whether it's a glitch in our measurements, a sign of deeper physics, or something even more profound, it forces us to confront an uncomfortable truth. The universe might still have surprises that humble our certainty. After all, if there's one thing history teaches us, it's that every time we think we've grasped our place in the cosmos finds a way to remind us we're just beginning to see the picture. At the heart of our galaxy, where stars crowd so thickly they blur into a golden haze, lies a gravitational monster, and it might not be the one you're thinking of. Sagittarius, a star, the 4 million solar mass black hole anchoring the Milky Way, dominates headlines, but it's only half the story. Surrounding it like an invisible crown is something far more elusive. A dark matter spike, a dense concentration of this mysterious substance packed so tightly that its gravity warps space itself. If dark matter is normally a faint cosmic mist, here it's a hurricane, swirling with such intensity that it defies everything we know about how matter should behave. Dark matter doesn't emit, absorb, or reflect light. It reveals itself only through gravity's pull. Normally, it's distributed in diffuse halos around galaxies. But near supermassive black holes, simulations predict something extraordinary. Dark matter particles, locked in a deadly dance with the black hole's gravity, would pile up into a steep, dense spike. At the Milky Way center, this spike could contain thousands of times more dark matter than equivalent volumes elsewhere in the galaxy. Picture a funnel with Sagittarius, a star, at its tip, concentrating dark matter like syrup dripping downward, thicker and darker the closer you get to the abyss. The irony is crushing. This spike might be one of the best places in the universe to study dark matter, if we could reach it, but the galactic center is a maelstrom of radiation, with particle speeds nearing light and magnetic fields strong enough to shred atoms. Any probe we send would be fried by X-rays, gamma rays, and cosmic rays long before it got close. Even telescopes struggle. The spike's location behind curtains of dust and stars makes observations like trying to spot a shadow in a blizzard. Yet hints persist. Some researchers hunt for indirect signals like gamma rays from hypothetical dark matter particles colliding and annihilating in the spike's crushing depths. Others track the orbits of hypervelocity stars, those flung outward by the black hole's gravity, looking for tugs that might betray the spike's presence. And then there's the strangest clue of all. The Milky Way's black hole is oddly quiet, emitting far less radiation than similar monsters in other galaxies. Could the dark matter spike be siphoning energy away, acting like a cosmic muffler? The truth is, we're groping in the dark, literally. This spike could rewrite the rules of particle physics, or it might not exist at all. Some models suggest black holes would scatter dark matter, preventing spike formation. Others argue we're misinterpreting the data entirely. But if it's real, it's a laboratory like no other, a place where the universe's most enigmatic substance is pushed to extremes we can't replicate anywhere else. One thing's certain, until we crack dark matter's code, the spike will remain a ghost in the machine, a whisper of all we don't yet understand, lurking just beyond the event horizon. The Milky Way doesn't travel through space alone. It's accompanied by a retinue of smaller galaxies, the most conspicuous being the Large and Small Magellanic Clouds. These satellite galaxies have orbited our own for billions of years, their delicate structures somehow surviving the Milky Way's crushing gravity. How? The answer lies in an invisible shield, a sprawling cloak of superheated gas known as the Magellanic Corona. This vast, faint halo stretches hundreds of thousands of light years around the clouds, acting like a cosmic buffer against the relentless tides of our galaxy's pull. What makes the corona so fascinating and so frustrating is its elusiveness. Unlike stars or even cold gas, this halo is made of ionized plasma, gas so hot it glows not in visible light but in far ultraviolet and X-rays. To our telescopes, it's nearly transparent, a ghostly veil detectable only through its subtle fingerprints on distant quasars. As light from these brilliant cosmic beacons passes through the corona, certain wavelengths are absorbed, revealing the halo's composition and structure in silhouette. It's like studying fog by observing how it dims a street lamp, except the lamp is billions of light years away, and the fog is a million-degree plasma. Without this protective envelope, the Magellanic Clouds would have been torn apart eons ago. As they orbit the Milky Way, the corona absorbs the brunt of our galaxy's gravitational forces, its hot gas dissipating energy that would otherwise shred the cloud's delicate spiral arms. Think of it as a cushion in a high-speed collision, only instead of milliseconds, the collision has lasted for cosmic epochs. Simulations show that without this buffer, the clouds would have already lost most of their gas, the raw material for new stars, leaving them as barren as many other Milky Way satellites. Yet the corona isn't just a shield, it's also a time capsule. Astronomers suspect much of its gas was stripped from the clouds themselves, ejected by supernova and stellar winds over billions of years. By studying its chemistry, we can trace the history of star formation in the Magellanic Clouds, uncovering how these galaxies evolved long before they crossed paths with the Milky Way. Some of its gas might even be primordial, a relic from the early universe untouched by stellar processes. The challenge is peeling back the layers of this invisible fortress. Even our most advanced telescopes struggle to map its full extent, leaving huge gaps in our understanding. Does the corona have a sharp edge, or does it fade gradually into intergalactic space? How much gas has it already lost to the Milky Way's pull? And perhaps most intriguingly, could similar coronas surround other satellite galaxies, a universal defense against their colossal hosts? One thing's certain, the Magellanic Corona is more than just a galactic accessory. It's a dynamic, ever-changing structure, a testament to the delicate balance of destruction and survival in the cosmos. And as we slowly unravel its secrets, we're reminded that sometimes the most powerful forces in the universe are the ones we can't even see. Not all cosmic voids are created equal. Nestled near the bustling Fornax cluster, a crowded metropolis of galaxies some 65 million light-years away, lies a small but baffling emptiness known as the Fornax Void. At just 30 million light-years across, it's a fraction the size of the Boötes Void, but what it lacks in scale, it makes up for in sheer defiance. This patch of space isn't just sparse, it's anomalously empty, challenging our understanding of how such voids form and evolve. Most cosmic voids are thought to emerge naturally from the universe's large-scale structure, like bubbles in a rising loaf of bread. Matter clusters into walls and filaments, leaving behind pockets of emptiness. But the Fornax Void sits uncomfortably close to a dense cluster, a region where gravity should have prevented such extreme emptiness from forming. It's as if you dug a pit in wet sand and found it stubbornly refusing to collapse, defying the weight pressing in from all sides. One leading theory suggests the void might be a fossil from an ancient cosmic battle, a relic of negative gravity. In the early universe, regions slightly less dense than their surroundings would have expanded faster, pushing matter away like a repulsive force. Over billions of years, this could have sculpted the Fornax Void into its current state, a bubble inflated by its own absence. But simulations struggle to replicate its precise properties, leaving astronomers to wonder if something more exotic is at play. Then there's the eerie silence. While most voids contain at least a handful of isolated galaxies, the Fornax Void is nearly pristine in its emptiness. The few galaxies that do linger here are oddly distorted, their shapes stretched as if fleeing some unseen menace. Some researchers speculate these might be refugees, galaxies flung into the void by past collisions or cluster interactions. Others propose the void itself is actively suppressing galaxy formation. Its extreme environment starving would be stars of the gas they need to ignite. The Fornax Void's greatest puzzle, though, is its proximity to the Fornax cluster. How could such a dense knot of galaxies coexist with such profound nothingness right next door? One provocative idea is that the cluster's gravity has been stealing matter from the void, siphoning gas and galaxies over billions of years like a cosmic thief. If true, the void might once have been far richer, its current emptiness the result of slow-motion plundering. Whatever the explanation, the Fornax void stands as a reminder that even the emptiest corners of the universe hold secrets. Its very existence forces us to question whether voids are passive absences or active players in shaping the cosmos. After all, in a universe ruled by gravity's pull, sometimes the most telling stories are written not by what's there, but by what's conspicuously missing. We've grown accustomed to thinking of space as a vast, evenly sprinkled expanse of galaxies. But what if the universe right outside our doorstep is emptier than it should be? This is the unsettling premise of the local hole, a curious underdensity stretching roughly 150 million light-years across, enveloping our Milky Way and its neighbors in a bubble that feels conspicuously sparse. Unlike the staggering emptiness of the Boötes void, this region isn't a complete desert, it's more like a thinning crowd at a concert, where the galaxies are still present but strangely spaced apart, as if something has been quietly siphoning them away. The existence of the local hole hinges on a paradox. While it's relatively nearby, making it prime territory for detailed study, it's also frustratingly difficult to confirm. One major obstacle is the Milky Way's own galactic disk, which acts like a smudged windshield, blocking our view of distant objects with thick bands of dust. This zone of avoidance means astronomers must rely on indirect methods to map the local hole's true extent, piecing together clues from redshift surveys and galaxy counts like detectives reconstructing a crime scene from partial fingerprints. Some argue this apparent underdensity might just be an illusion, a trick of cosmic camouflage where dust and gas obscure galaxies that are actually there. But the evidence for the local hole's reality keeps mounting. Measurements of galaxy motions reveal a peculiar trend. They're streaming away from this region as if repelled by its emptiness. This aligns with the peculiar velocity of our local group, the collective motion of the Milky Way and Andromeda, which appears to be influenced by the hole's gravitational deficit. It's like standing in a valley and feeling a subtle breeze. You might not see the wind's source, but you can sense its presence. Even more intriguing is what the local hole might tell us about dark energy. If this void is real, its underdensity could slightly accelerate the expansion of space within it, a miniature echo of the force driving the universe apart on cosmic scales. Some models suggest such voids act as negative masses, their gravity working in reverse to push matter outward rather than pulling it in. If true, the local hole isn't just an absence, it's an active participant in shaping the cosmos, a reminder that emptiness can exert its own strange influence. Yet skeptics remain unconvinced. Alternative explanations point to the quirks of large-scale structure formation, where filaments and walls of galaxies naturally leave behind gaps. Could the local hole simply be one of many temporary fluctuations in the cosmic web, destined to fill in over time? Or does its persistence hint at something deeper, a flaw in our models of how matter clusters across the universe? The debate encapsulates a larger truth. Sometimes the hardest mysteries to solve are the ones closest to home. The local hole challenges us to question not just what we see, but how we see it, to distinguish between the universe's true face and the shadows our own galaxy casts upon it. Until we peer through the dust with sharper eyes, this nearby enigma will remain suspended between discovery and doubt, a cosmic riddle written in the negative space around us. Deep in the northern sky, hidden among the constellations of Hercules and Corona Borealis, lies a structure so immense it strains the limits of our cosmic comprehension. This is the Hercules-Corona Borealis Great Wall, a sprawling filament of galaxies stretching an almost inconceivable 10 billion light-years from end to end. To put that into perspective, if you could travel at the speed of light, it would take you twice the current age of Earth just to cross it. This isn't just a cluster or a supercluster, it's a monster, a cosmic web thread so vast it makes the Milky Way look like a speck of dust caught in a galactic spider's silk. What makes this structure so controversial isn't just its size, it's the way it seemingly defies one of cosmology's most sacred principles, the cosmological principle. This foundational idea states that on the largest scales, the universe should appear roughly uniform, with matter distributed evenly like raisins in a loaf of bread. Yet here we have the Great Wall, a structure so colossal it occupies nearly a tenth of the observable universe's diameter. It's as if we've stumbled upon a mountain range taller than the atmosphere, something that, by all rights, shouldn't exist. Astronomers first detected the Great Wall in 2013, while mapping gamma-ray bursts the violent deaths of massive stars. These bursts act like cosmic lighthouses, their brief flashes revealing the distribution of matter across the universe. When researchers plotted their locations, a pattern emerged, an eerie concentration of bursts tracing an arc across the sky, hinting at an underlying structure of unprecedented scale. Follow-up observations confirmed it a vast, interconnected network of galaxy clusters, superclusters, and dark matter, woven into a single, unimaginably large ribbon. The discovery sent shockwaves through the astrophysics community. If the Great Wall is real, it forces us to reconsider how such colossal structures could form in the time since the Big Bang. Gravity works slowly. For matter to clump on this scale in just 13.8 billion years pushes the limits of our models. Some theorists argue it might be a statistical fluke, a chance alignment of smaller structures that only appears connected from our vantage point. Others suggest it could be evidence of exotic physics, like primordial quantum fluctuations frozen into the fabric of space-time, seeding irregularities far larger than we thought possible. Then there's the haunting possibility that the Great Wall isn't alone. If structures this vast can exist, what's stopping even larger ones from lurking just beyond our current observational limits? Future telescopes, like the James Webb's successors, might reveal a universe far more clumpy and hierarchical than we ever imagined, a cosmic web where the threads themselves are galaxies wide. For now, the Hercules-Corona Borealis Great Wall stands as both a marvel and a warning. It reminds us that the universe, for all our mapping and modeling, still holds surprises that challenge the very frameworks we use to understand it. Whether it's a flaw in our principles or a sign of deeper complexity waiting to be uncovered, one thing is certain: the cosmos refuses to be neatly boxed. And that's exactly what makes it so thrilling to explore. Before the Hercules-Corona Borealis Great Wall shattered records, there was the Sloan Great Wall, a galactic behemoth that once held the title of the largest known structure in the universe. Discovered in 2003 by the Sloan Digital Sky Survey, this cosmic ribbon spans a staggering 1.4 billion light-years, weaving through the constellations of Leo and Virgo like a river of galaxies frozen in time. Though dwarfed by its Hercules-Corona Borealis successor, the Sloan Wall remains a milestone in cosmology, a relic from an era when we first began grasping just how far the universe's architecture could stretch. What makes the Sloan Great Wall so fascinating isn't just its size. It's the way it forced astronomers to confront the limits of the standard model of cosmology. According to this framework, the universe's large-scale structure should resemble a sponge, a network of filaments and voids, but without any single structure dominating the scene. The Sloan Wall pushed that assumption to the brink. Here was a chain of superclusters so vast it seemed to bend the rules, challenging our understanding of how quickly gravity could assemble matter after the Big Bang. If galaxies are supposed to be evenly distributed like sprinkles on a cupcake, the Sloan Wall was an unbroken line of frosting defying the pattern. Yet the Sloan Wall differs from the Hercules-Corona Borealis structure in one crucial way: it's closer. At just 1 billion light-years away, it's near enough for telescopes to dissect its anatomy in detail. Observations reveal it isn't a solid wall at all, but a filamentary scaffold, a loose braid of galaxy clusters connected by tenuous threads of dark matter. Some regions are densely packed, while others are nearly empty, like cities linked by rural highways. This patchwork structure hints at how such colossal forms emerge, not as monolithic blocks, but as cosmic rivers sculpted by gravity over eons. The real tension arises when we compare these walls to simulations. In virtual universes generated by supercomputers, structures as vast as the Sloan Wall are rare but possible. The Hercules-Corona Borealis version, however, strains even those limits, appearing in fewer than 1% of simulated cosmoses. Could this mean our universe is an outlier, a statistical fluke on a grand scale, or worse? Does it suggest gaps in our models, like overlooked forces or quirks in dark energy's behavior? Some theorists argue these walls might be optical illusions, the chance alignment of smaller structures viewed from the perfect angle. Others propose they're evidence of primordial sound waves frozen in time, relics from the universe's first second when density fluctuations etched their imprint into space itself. The Sloan and Hercules-Corona Borealis walls aren't just cosmic curiosities, they're stress tests for our most fundamental theories. Each new discovery of a larger structure peels back another layer of our assumptions, revealing how little we truly know about the universe's blueprint. And as telescopes grow sharper, who's to say we won't find something even more immense, lurking just beyond our current view? After all, the history of astronomy is a story of ceilings shattered, of horizons that seemed finite until we reached them, only to find the universe had been hiding something bigger all along. If the Eridanus cold spot feels like a shadow cast across the cosmos, its true influence might be far stranger than we ever imagined. Recent studies suggest this enigmatic region could be acting not just as a void, but as a cosmic repeller, a place where galaxies aren't merely sparse but actively pushed away. Imagine a hidden hand in the fabric of space-time, gently but firmly shoving entire galaxy clusters outward, as if the universe itself were allergic to this patch of emptiness. This isn't just gravity's pull in reverse, it's a phenomenon that challenges our very understanding of what drives the large-scale motion of the cosmos. The idea of a repeller sounds like science fiction, but the evidence is mounting. Astronomers tracking the peculiar velocities of galaxies, their deviations from the smooth expansion of the universe, have noticed a consistent pattern. Thousands of galaxies are streaming away from the cold spot's general direction, as if fleeing some invisible threat. The simplest explanation, the cold spot isn't just an absence of matter. It's a region of negative gravity where the lack of mass creates a kind of cosmic slope that galaxies naturally roll down. In other words, it's not pulling them in, it's letting them go. This concept flips dark energy on its head. While dark energy drives the universe's accelerated expansion uniformly, the cold spot repeller would be a localized anomaly, a pocket where the push is stronger than average. Some theorists suggest it could be a sign of dark energy's uneven distribution, clumping in ways we never anticipated. Others argue it might be evidence of something even more exotic, a quantum bubble, a relic from the universe's infancy where the laws of physics temporarily warped, leaving behind a scar that still repels matter today. Picture a blister on the surface of space-time, one that never quite healed, and now everything avoids touching it. Yet skepticism abounds. Critics point out that the repeller's effect could simply be the cumulative tug of known superclusters elsewhere, their gravity creating the illusion of a push. Alternatively, the cold spot's apparent repulsion might be a quirk of how we map galaxy motions, a cosmic mirage caused by incomplete data. After all, the universe is a messy place, and teasing apart its true motions from our limited perspective is like trying to reconstruct a storm's path from a handful of scattered weather vanes. What makes this mystery so tantalizing is the stakes. If the Cold Spot Repeller is real, it could reshape our understanding of cosmic dynamics, revealing forces beyond dark energy that sculpt the universe's large-scale flows. If it's an illusion, it exposes gaps in our models, reminding us how much we still don't know about the interplay between gravity, dark matter, and dark energy. Either way, the cold spot continues to defy easy explanation, not just as a cold patch in the cosmic microwave background, but as a potential architect of motion on the grandest scales. The universe, it seems, has a way of staying one step ahead of our curiosity. The dark flow's relentless tug on galaxy clusters raises a haunting question: what monstrous force beyond the observable universe could be steering them? Our cosmic horizon, the farthest light we can see, lies just 46 billion light-years away, the limit set by the age of the universe and the speed of light. Yet the dark flow hints at something farther, a gravitational shadow so vast it defies explanation. Is it an unimaginably dense supercluster from a neighboring region of space-time, a relic of the Big Bang's asymmetry, or evidence of something even stranger, like a parallel universe brushing against our own? One compelling idea points to primordial inhomogeneities, lumps in the infant universe so colossal they shape the cosmos on scales we've only begun to glimpse. Inflation theory suggests that quantum fluctuations in the universe's first trillionth of a second were stretched to cosmic proportions, seeding galaxies and voids. But what if some fluctuations were too large, imprinting irregularities beyond our horizon? These could have birthed megastructures with gravity strong enough to reach across the observable universe, pulling galaxies toward them like magnets hidden behind a veil. Then there's the multiverse angle. If our universe is one bubble in an infinite foam of others, each with its own physics and dimensions, could a nearby bubble be warping space-time at the border? Picture two soap films merging. The tension where they meet might distort gravity in ways we perceive as dark flow. Some string theory models even suggest higher dimensional brain worlds floating in a bulk space, their gravity leaking into our universe. If true, dark flow might be the first whiff of a reality where the laws of physics are fundamentally alien. Yet skeptics argue for simpler answers. The flow could stem from errors in how we measure galaxy velocities or map cosmic microwave background distortions. Or perhaps dark energy, the mysterious force accelerating the universe's expansion, isn't uniform but clumped in ways we don't yet understand, creating phantom currents in the cosmic ocean. The truth might lie beyond our current tools. To probe the dark flow's source, we'd need gravity to carry information faster than light, something Einstein's relativity forbids. Until we crack quantum gravity or detect echoes of collisions with other universes, this mystery will linger at the edge of imagination. Dark flow doesn't just challenge our models, it dares us to consider that the universe we see might only be the preamble to a story we can't yet read. The cosmic microwave background is supposed to be a random mosaic, a scatter of hot and cold spots left over from the Big Bang's turbulent aftermath. But when scientists peeled back the layers, they found something that sent chills down the spine of cosmology. The largest scale fluctuations in the CMB aren't just random. They're aligned, as if some hidden hand had gently brushed the universe's baby picture, leaving subtle strokes across the sky. These patterns, known as the quadrupole and octupole alignments, defy expectations so profoundly that they've sparked radical theories, from a finite universe curled in on itself to echoes of an era before time began. At the heart of the mystery are the lowest multipoles, the quadrupole and octupole, which represent the CMB's broadest, smoothest undulations. When astronomers mapped them, they expected chaos, a jumble of directions with no preferred orientation. Instead, the quadrupole's hot and cold spots line up suspiciously with the octupoles, their axes weaving through space like faintly drawn arrows pointing toward the same invisible target. The odds of this happening by chance, less than 1 in 1,000. It's as if the universe's very first moments were imprinted with a cosmic fingerprint we're only now deciphering. For some theorists, these alignments suggest the universe might be finite, a closed geometry where space wraps around itself like the surface of a four-dimensional balloon. In such a cosmos, the largest fluctuations would naturally sync up, their patterns repeating like echoes in a spherical room. Others propose these alignments are scars from before inflation, the brief but explosive period when the universe expanded faster than light. If inflation didn't start perfectly smoothly, if it was lopsided or bumpy, it could have left behind ripples in the CMB that still whisper of that primordial imbalance. Then there's the truly radical idea that the alignments aren't cosmological at all. They might be artifacts of our local environment, distortions caused by the Milky Way's gravity bending the CMB's light as it travels to us, or even contamination from dust in our own galactic backyard. Critics of the alignment anomaly point out that subtracting foreground interference can weaken the signal, leaving it hovering at the edge of statistical significance. But even after meticulous cleaning, the pattern persists, gnawing at the edges of the standard model. Perhaps the most haunting possibility is that these alignments are glimpses of something beyond our universe's birth, a shadow of the multiverse. In certain theories, collisions between neighboring bubble universes could leave bruises on the CMB, subtle asymmetries that imprint directional preferences. Others suggest the alignments might encode the universe's spin, a relic rotation from its earliest moments that somehow survived inflation's smoothing effect. Whatever their origin, the CMB's alignments are more than just cosmic curiosities, they're cracks in the foundation of our understanding. Each new analysis peels back another layer, revealing just how much we still don't know about the universe's first moments. And if one thing's certain, it's that the cosmos rarely serves up anomalies without a reason. Sometimes the most profound discoveries begin with realizing the data isn't just noisy, it's trying to tell us something. Rising from the heart of our galaxy like twin titans, the Milky Way's radio bubbles are a recent and startling discovery, colossal structures of charged particles stretching 25,000 light-years above and below the galactic plane. Unlike their better-known cousins, the Fermi bubbles, which glow in high-energy gamma rays, these radio behemoths emit faint but sprawling signals detectable only at radio wavelengths. They're ghostly echoes of some ancient cataclysm, their delicate filaments and vast arcs hinting at a violence that once rocked the Milky Way's core. What makes these bubbles so perplexing is their sheer scale, matching the Fermi bubbles in size but revealing an entirely different facet of the same event. While the Fermi bubbles are thought to be the aftermath of a gargantuan black hole feast, where Sagittarius, a star, devoured a torrent of gas and spat out jets of energy, the radio bubbles suggest something more complex. Their structure, laced with intricate threads and bubble-like subregions, points to multiple eruptions, as if our galaxy's central black hole has been periodically coughing up energy like a cosmic volcano. One leading theory suggests the bubbles are relics of a past Fermi-like event, where the initial explosion created shockwaves that pushed gas outward, leaving behind cavities that later filled with radio-emitting particles. Over millions of years, weaker outbursts from Sagittarius, a star, might have re-energized these cavities, sculpting the intricate patterns we see today. It's like finding the charred remains of a forest fire, only to realize smaller fires kept flaring up long after the first blaze. But there's a twist: the radio bubbles don't perfectly align with the Fermi bubbles. Some regions overlap while others veer off at odd angles, as if shaped by forces beyond just the black hole's fury. This has led to alternative explanations, like collisions between galactic winds, the outflow of gas from countless stars, and the Milky Way's halo of dark matter. Imagine two weather fronts colliding. The turbulence creates eddies and ripples, much like the bubble's intricate radio filaments. The most tantalizing possibility is that these structures are intertwined chapters of the same story. The Fermi bubbles could represent the initial, violent explosion, while the radio bubbles are the slower, lingering aftermath, a cosmic fossil recording how energy dissipates over eons. If true, studying them together could unlock secrets about how supermassive black holes shape their galaxies, not just in single catastrophic events, but in cycles of eruption and quiet. Yet mysteries remain. Why do the radio bubbles appear so much fainter than their gamma-ray counterparts? Are they truly ancient, or could they still be actively fed by the black hole's quieter outbursts? And most intriguingly, could other galaxies harbor similar radio ghosts, their own histories written in structures we've only just learned to see? The Milky Way's radio bubbles are more than just celestial curiosities. They're a reminder that even our home galaxy still has secrets buried in plain sight. With every new observation, we're piecing together a saga of cosmic violence and rebirth, one that's been unfolding silently above our heads for millions of years. And if there's one lesson these bubbles teach us, it's that the universe never truly forgets. Its past is always whispering if we know how to listen. There's a boundary around us, one we'll never cross, no matter how far our telescopes peer into the depths of space. This is the edge of the Hubble volume, the observable universe's ultimate limit, a sphere centered on Earth with a radius of roughly 46 billion light-years. Beyond it, the cosmos retreats from us faster than light can travel, forever placing those regions out of reach. It's not just a physical barrier, it's a philosophical reckoning, a reminder that some mysteries are written in places where no signal, no probe, no human ingenuity will ever reach. The Hubble volume's edge isn't a wall or a void, it's a horizon, much like the curve of the Earth hiding distant ships from view. But instead of ocean blocking our sight, it's the expansion of space itself. Galaxies near this boundary are being carried away by the universe's accelerating growth, their light stretched into useless infrared whispers before fading entirely. Even if we could teleport to that edge today, we'd watch the cosmos beyond it vanish like a mirage, receding into darkness as space's relentless stretch outruns the speed of light. This isn't science fiction, it's the cold, hard consequence of living in an expanding universe with strict cosmic speed limits. So what lies beyond? The unobservable universe could be anything more of the same galaxies and voids we see here, or something entirely alien. Some theories suggest exotic variations in physical laws, regions where gravity repels instead of attracts, or bubbles of space-time with extra dimensions curled into existence. Others propose a fractal cosmos, repeating structures on scales so vast they dwarf even the Hercules-Corona Borealis Great Wall. Then there's the multiverse hypothesis. Our Hubble volume might be one bubble in an infinite foam of universes, each with its own unique physics, forever separated by stretches of inflationary space where no light can bridge the gap. But here's the twist: the Hubble volume's edge isn't static. As time passes, the observable universe shrinks. Distant galaxies slip beyond the horizon as expansion severs their connection to us, leaving future astronomers with a sky more barren than our own. In 1 trillion years, the Milky Way could be alone in a void of blackness, every other galaxy having vanished like footsteps washed away by a rising tide. This isolation forces us to confront a chilling truth: we're living in a privileged sliver of time, one where the cosmos is still generous enough to show us its wonders. If there's a lesson in the Hubble volume's edge, it's humility. We're trapped in a cosmic fishbowl, limited not by technology or imagination, but by the fundamental rules of reality. Yet, even within these confines, the universe has offered up staggering beauty: galaxies, black holes, dark energy, all woven into a tapestry we're only beginning to decode. The unobservable beyond might forever be a blank page, but that's what makes it so tantalizing. Somewhere past that horizon, the universe is writing stories we'll never read. And perhaps that's exactly how it's meant to be. At the smallest scales imaginable, far beneath atoms, quarks, even the reach of our most powerful microscopes, space-time itself stops being smooth and instead churns like a turbulent ocean. This is the realm of quantum foam, a seething, chaotic froth where space and time lose all semblance of order, bubbling with virtual particles that flicker in and out of existence faster than the blink of an eye. If you could shrink down to the Planck scale, a length so tiny it's a million billion times smaller than a proton, you'd witness reality itself unraveling into a storm of uncertainty, where the very concepts of here and now cease to have meaning. The idea of quantum foam emerged from the clash between Einstein's general relativity and quantum mechanics. Relativity paints spacetime as a smooth, stretchy fabric warped by mass and energy. Quantum mechanics, on the other hand, insists that at the tiniest scales, everything is unpredictable, governed by probabilities rather than certainties. Marrying these two theories leads to a bizarre prediction. Spacetime shouldn't stay smooth. Instead, it should fluctuate wildly, twisting into microscopic wormholes, knots, and voids that form and vanish in fractions of a nanosecond. Picture the surface of a boiling pot, but instead of bubbles, you're seeing space and time itself bubbling, a foam where the laws of physics as we know them are constantly being rewritten. What makes quantum foam so tantalizing and so frustrating is that we may never directly observe it. The Planck length isn't just small, it's so far beyond our current technological limits that probing it would require a particle accelerator the size of our galaxy. Even if we could build one, the foam's fluctuations happen on timescales so brief they're practically instantaneous. Some theorists argue that indirect signatures might lurk in high-energy cosmic rays or the faint echoes of black hole mergers, like ripples from a stone tossed into this cosmic froth. But for now, quantum foam remains a ghost in the equations, a mathematical specter haunting the intersection of our two most successful and stubbornly incompatible theories of reality. Yet if quantum foam is real, the implications are staggering. It could mean that spacetime isn't fundamental at all, but emergent, a sort of illusion created by deeper, more chaotic processes, like how the smooth surface of water hides the frantic dance of molecules beneath. Some models even suggest that wormholes in this foam might connect distant parts of the universe, threading space with hidden shortcuts. Others propose that dark energy, the mysterious force accelerating cosmic expansion, might stem from the foam's relentless energy, a sort of background static humming beneath existence itself. The wildest idea, quantum foam might not just be a quirk of our universe. It could be the seed of entirely new ones. In certain multiverse theories, bubbles of spacetime can pinch off from the foam, inflating into full-fledged universes with their own laws of physics. Our entire cosmos, in this view, might be one such bubble, a chance fluctuation that grew beyond its quantum cradle. For now, quantum foam remains one of the most enigmatic frontiers in physics, a realm where space and time dissolve into chaos, where reality's rulebook is shredded and rewritten at every moment. It's a reminder that the universe, for all its grand structures and vast emptiness, might ultimately be built on something far stranger, a storm in the void, a dance of uncertainty at the edge of nothingness. Among the most elusive particles in the universe, neutrinos are ghosts zipping through planets, stars, and even you at nearly the speed of light, barely leaving a trace. Billions pass through your fingernail every second, yet detecting even a handful requires massive, painstakingly calibrated experiments buried deep underground. But there are places where these phantoms do something even stranger. They disappear. Welcome to the neutrino deserts, regions of space or energy ranges where neutrinos vanish without explanation, leaving gaps in our detectors like footprints erased by an invisible tide. These deserts aren't barren wastelands but cosmic anomalies that defy the standard model of particle physics. Normally, neutrinos oscillate, changing between three known flavors: electron, muon, and tau as they travel. But in certain experiments, particularly those studying neutrinos fired from particle accelerators or emitted by nuclear reactors, some neutrinos seem to simply vanish mid-flight. The numbers don't add up. Detectors catch fewer neutrinos than predicted, as if the particles have stepped into a hidden dimension or transformed into something entirely unseen. This missing neutrino problem has led physicists to a radical idea: sterile neutrinos. Unlike their ordinary cousins, sterile neutrinos wouldn't interact via the weak nuclear force, the usual neutrino handshake with matter. They'd feel only gravity, slipping through the universe like shadows through a screen door. If they exist, sterile neutrinos could explain not just the disappearance of ordinary neutrinos, but one of cosmology's biggest puzzles: dark matter. These phantom particles, too heavy and slow-moving to detect directly, might be lurking in vast clouds around galaxies, their collective gravity shaping the cosmos from the shadows. The evidence is tantalizing but messy. Some experiments, like the LSND and mini Boötes collaborations at Fermilab, have reported anomalous neutrino oscillations hinting at sterile neutrinos. Others, like the ice cube detector buried in Antarctic ice, see no such signal. The discrepancy has split the physics community, with some calling sterile neutrinos a near certainty and others dismissing them as statistical mirages. What makes neutrino deserts so compelling is their potential to rewrite physics. If sterile neutrinos are real, they demand a fourth flavor, a particle outside the standard model's tidy framework. They might also bridge the gap between particle physics and cosmology, offering a dark matter candidate that doesn't rely on hypothetical WIMP or actions. Imagine a universe where the very particles we've overlooked, the ones that refuse to interact, are the hidden architects of everything, yet the deserts remain stubbornly uncharted. Without direct detection, sterile neutrinos linger in limbo, their existence inferred only by absence. Future experiments, like the Deep Underground Neutrino Experiment (DUNE), aim to settle the debate by firing neutrinos through 800 miles of Earth to see how many arrive and how many are lost along the way. The results could either crack open the standard model or leave us staring deeper into the void, wondering where the ghosts have gone. Neutrino deserts aren't just about missing particles, they're about the edges of knowledge. Every gap in the data, every unexplained disappearance is a clue waiting to be deciphered. And if history is any guide, the universe's quietest corners often hold the loudest secrets. Dark matter is often depicted as a smooth, invisible cloak draped around galaxies, but what if its true form is far more jagged? Lurking in the hearts of galactic halos, theorists predict razor-thin spikes of weakly interacting massive particles, cosmic needles in a haystack where the hay is already invisible. These WIMP cusps are density spikes so extreme that they could contain more dark matter than entire galaxies, packed into regions smaller than our solar system. Yet despite their staggering mass, they remain almost impossible to detect, hiding in plain sight while warping the cosmos with their silent gravity. The problem isn't just that WIMP refuse to interact with light, it's where they're concentrated. In most simulations, dark matter forms diffuse clouds around galaxies, its particles scattered like dust in a windstorm. But near the centers of halos, particularly around supermassive black holes, gravity's pull could compress WIMP into dense, steep cusps where particle densities skyrocket. Picture a whirlpool funneling water downward, only instead of liquid, it's dragging in streams of invisible matter, packing them tighter as they spiral inward. Under the right conditions, these cusps might even collapse further, forming microscopic black holes or igniting bursts of gamma rays from particle collisions. Yet for all their dramatic potential, WIMP cusps frustrate every attempt at detection. Traditional methods like underground labs, which hunt for rare collisions between WIMP and ordinary atoms, struggle because the cusps occupy such infinitesimal volumes. Even if a cusp sits at the Milky Way's core, its signal drowns in the noise of cosmic rays and other background interference. Indirect detection isn't much easier. Telescopes scanning for gamma rays from annihilating WIMP see only ambiguous blurs, impossible to distinguish from pulsars or other energetic phenomena. The real irony, these cusps might be self-destructing. Some models suggest that as WIMP pile up, their annihilation rates increase, burning away the cusp as fast as it forms. It's like trying to light a fire in a hurricane. The very process that could reveal the cusp's existence might also erase it before we can look. Other theories propose that supermassive black holes disrupt cusps entirely, their gravity scattering particles like a spoon stirring cream into coffee. But the most tantalizing clue might come from stars. Near the Milky Way center, astronomers have spotted stars orbiting at bizarre speeds, their paths suggesting a gravitational tug far stronger than the black hole alone can explain. Could a WIMP cusp be yanking them off course, or are we seeing the fingerprints of something even stranger? Until we crack dark matter's code, these cusps will remain ghostly landmarks on a map we can't yet read, a reminder that the universe's most massive structures might also be its most elusive. The universe isn't a scatter of disconnected islands, it's a vast, intricate network, a tapestry woven from threads of superheated gas stretching millions of light years between galaxies like a cosmic spider's silk. These filaments of the cosmic web glow faintly with the energy of ancient collisions, charged particles tracing the hidden scaffolding upon which all visible matter is hung. Yet for all their grandeur, these luminous threads remain one of the most elusive structures to map, their delicate light drowned out by the brilliance of stars and galaxies they connect. Imagine trying to photograph a whisper in a hurricane. That's the challenge astronomers face when studying these filaments. Their light comes from warm, hot intergalactic medium, a plasma so diffuse it barely registers against the blackness of space. At temperatures between 10,000 and 10 million degrees, this gas emits X-rays and ultraviolet light, wavelengths our atmosphere blocks entirely. To catch even a glimpse, we must launch telescopes beyond Earth's veil, like the European Space Agency's XMM Newton or Japan's Hitomi satellite, instruments fine-tuned to capture these faintest of cosmic signatures. Even then, the data is often drowned in noise, like trying to hear a single violin in a roaring stadium. What makes these filaments so crucial and so maddeningly hard to study is their role as the universe's hidden plumbing. They funnel gas into galaxies, fueling star birth and shaping cosmic evolution. Simulations suggest over half the ordinary matter in the universe resides in these threads, a reservoir of protons and electrons that's been missing from our inventories until recently. Yet when astronomers tally up all the visible stars, gas, and dust, they've historically come up short. The filament's faint glow might solve this missing baryon problem, revealing where the universe stashed its ordinary matter. Mapping them, however, demands ingenuity. One clever workaround uses quasars' distant, ultra-bright galactic cores as backlights. As quasar light passes through filaments, certain wavelengths get absorbed, leaving spectral fingerprints in the light we detect. It's like studying a stained glass window by analyzing the colors it filters from sunlight. Another approach hunts for the Sunyaev-Zeldovich effect, where filaments subtly distort the cosmic microwave background as it passes through them, leaving telltale shadows in the universe's oldest light. Even with these techniques, the cosmic web resists full revelation. Its filaments are too vast, their gas too thin, their signals too easily confused with foreground interference. New telescopes like the upcoming Athena X-ray Observatory promise sharper views, but for now, these threads remain half-seen ghosts, their full structure hovering just beyond our grasp. Yet every patch we do map reveals surprises, regions where filaments knot unexpectedly, or where gas flows contradict predictions, hinting at processes we've yet to understand. The cosmic web's filaments aren't just connections between galaxies, they're the universe's circulatory system, the veins through which the raw material of existence flows. And as we slowly chart their courses, we're tracing the very channels that shaped everything from the smallest star to the largest supercluster, uncovering the hidden currents that bind the cosmos together. Even in the deepest voids of space, where galaxies are scarce and darkness stretches for millions of light years, the universe is never truly empty. Beneath the stillness lurks a seething, invisible turmoil, quantum fluctuations, where particles and energy burst into existence for fleeting moments before vanishing again. These ephemeral flickers, governed by the bizarre rules of quantum mechanics, suggest that a void isn't just an absence of matter. It's a stage for some of reality's most fundamental performances. At the heart of this phenomenon lies Heisenberg's uncertainty principle, which dictates that empty space can never settle into perfect stillness. Instead, it thrums with virtual particles, electron-anti-electron pairs, quarks, even miniature black holes popping in and out of existence so quickly they're nearly impossible to detect. Picture a quiet lake's surface. From a distance it appears smooth, but up close you'd see countless tiny ripples constantly forming and dissolving. The quantum void is like that, but scaled down to the realm of atoms and smaller, where the fabric of spacetime itself churns with unseen activity. Some physicists speculate these fluctuations could be far more than microscopic static. They might hold the key to cosmic creation. In certain models of inflationary theory, a particularly energetic quantum jitter in the early universe could have triggered a runaway expansion, birthing not just our universe but an endless multiverse of others. It's as if the quantum foam isn't just froth, it's a bubbling cauldron of potential realities, each fluctuation a possible doorway to another cosmos with its own laws of physics. The void, in this view, isn't dead space. It's a nursery for universes we'll never see. Yet there's a darker possibility. If these fluctuations grow intense enough, perhaps near the core of a black hole or in the extreme environment of the early universe, they might twist spacetime into knots, birthing temporary wormholes or regions where time itself flows backward. Some theorists suggest this could explain anomalies like dark energy, the mysterious force accelerating the universe's expansion. Maybe what we perceive as dark energy is actually the cumulative effect of quantum ripples stretching the cosmos from within, like invisible hands tugging at the seams of reality. The challenge is testing these ideas. Quantum fluctuations operate on scales far smaller than anything our instruments can probe directly, their effects too subtle to measure in most laboratory settings. Yet indirect hints might lie in the cosmic microwave background's faintest irregularities, or in the precise behavior of entangled particles in quantum experiments. Future technologies like quantum gravity detectors or advanced particle colliders could offer glimpses, but for now, the void's quantum dance remains a breathtaking theory painted in the language of mathematics. Whether these fluctuations are cosmic seeds, space-time distortions, or something even stranger, one thing is clear: the emptiest places in the universe are anything but inert. They're alive with possibility, humming with energies we're only beginning to imagine. And if there's a lesson in quantum uncertainty, it's that the universe reserves its greatest surprises for the places we least expect to find them. Black holes have long been the ultimate cosmic vaults, places where matter, light, and even the laws of physics seem to vanish without a trace. But what happens to the information carried by all that swallowed material? According to quantum mechanics, information can never truly be destroyed, only scrambled beyond recognition. Yet black holes, with their monstrous gravitational pull and inescapable event horizons, appear to break this cardinal rule. This is the black hole information paradox, a puzzle so profound it has split the physics community for decades, and the answers might rewrite our understanding of reality itself. At the heart of the paradox is a simple but devastating question. When a black hole evaporates over eons via Hawking radiation, what happens to the quantum information of the particles it consumed? Hawking's calculations initially suggested this information is erased forever, a violation of quantum unitarity, the principle that the universe must keep perfect track of every particle's state. Imagine burning a book and claiming its words could never be recovered, even in principle. That's the crisis black holes seem to introduce. The implications ripple beyond astrophysics, threatening the foundations of quantum theory and our entire framework for predicting how the universe evolves. Enter the firewall paradox, a radical idea that suggests the event horizon might not be the smooth, uneventful boundary Einstein's relativity predicts. Instead, it could be a seething wall of high-energy particles, a literal inferno that incinerates anything crossing it. This firewall would resolve the information paradox by ensuring data never actually enters the black hole. It's destroyed at the horizon, preserving quantum mechanics but upending relativity. The catch: relativity insists an observer falling into a black hole should notice nothing unusual at the horizon, no fire, no drama. The laws of physics shouldn't hinge on who's watching. Another solution comes from holography, the mind-bending notion that all the information in a black hole isn't lost inside it. It's smeared across its surface like a cosmic hard drive. Just as a two-dimensional hologram can encode a 3D image, the event horizon might store a perfect, scrambled record of everything that fell in. When the black hole radiates away, this information could slowly leak back out, hidden in the quantum correlations of Hawking radiation. It's as if the universe keeps receipts, ensuring no data is ever truly lost, just transformed beyond immediate recognition. But what about the singularity itself? At the black hole's core, gravity becomes infinite, space-time curvature rips apart, and our equations fail spectacularly. No signal, no light, no theory we currently possess can describe what happens there. Some models suggest singularities might not be points but fuzzy, quantum mechanical blurs where space and time dissolve entirely. Others propose they're gateways to other universes, cosmic backdoors hidden behind the ultimate veil. The truth is, we're groping in the dark. The information paradox forces us to confront the limits of both quantum mechanics and general relativity, hinting at a deeper theory that unifies them. Whether the answer lies in firewalls, holograms, or something stranger, one thing is certain: black holes aren't just cosmic vacuum cleaners, they're laboratories for the most extreme physics imaginable. And every solution we propose doesn't just solve a paradox, it rewrites the rules of existence. At the very beginning, or more accurately, before beginnings had any meaning, there was the singularity. This isn't just a point in space and time. It's the breakdown of space and time, a realm where all known laws of physics dissolve into chaos. The Big Bang's singularity is the ultimate cosmic no-go zone, a place where density and temperature skyrocket to infinity, where the very concepts of before and after lose their grip. Even black holes, with their crushing singularities, are tame compared to this. At least a black hole's singularity is hidden behind an event horizon. The Big Bang's is the event horizon of reality itself, a wall beyond which science as we know it cannot see. What makes this singularity so impossible to explore isn't just its extreme conditions, it's the absence of tools to describe it. Einstein's general relativity, which brilliantly maps the curvature of spacetime around massive objects, buckles under the singularity's infinite pressures. Quantum mechanics, which governs the subatomic world, offers no help either because gravity, the dominant force here, still resists integration into quantum theory. It's like trying to decode a language with no alphabet, no grammar, just raw, unfiltered paradox. This breakdown has led physicists to propose radical alternatives. One compelling idea comes from loop quantum gravity, which suggests spacetime isn't smooth and continuous but woven from tiny, indivisible loops. At the Big Bang's singularity, these loops might have reached maximum compression, then bounced, creating our universe from the rebound of a prior collapsing one. Imagine a cosmic rubber band stretching to its limit, then snapping back with enough force to birth everything we know. This Big Bounce theory elegantly sidesteps the singularity's infinities, replacing them with a cyclical universe where time has no true start or end. Then there's string theory's approach, where the singularity isn't a point but a multidimensional membrane colliding with another in a higher dimensional space. In this scenario, the Big Bang wasn't an explosion but a cosmic collision, a shockwave reverberating through dimensions we can't perceive. It's as if our universe is the echo of a far larger event, one that left its fingerprint in the distribution of galaxies and the faint whispers of the cosmic microwave background. But perhaps the most mind-bending possibility is that the singularity never existed at all. That time itself is an emergent property, something that crystallized as the universe cooled. In this view, asking what came before the Big Bang is like asking what's north of the North Pole. Time, as we understand it, might simply not apply. The singularity then becomes less a physical place and more a mathematical artifact, a signpost reading, "Here be dragons," at the edge of our understanding. The singularity's mystery forces us to confront the limits of human knowledge. Every theory we've devised bounces, brains, emergent time, is a makeshift bridge over an abyss we can't yet cross. Future breakthroughs in quantum gravity or experiments probing the universe's earliest moments might one day illuminate this shadowed realm. But for now, the Big Bang's singularity remains the ultimate cosmic secret, a reminder that some frontiers aren't just unexplored, they're fundamentally unexplorable by nature. And in that impossibility lies its allure, the tantalizing sense that the universe's deepest truths are still waiting, just beyond the edge of time. From the Great Attractor's unseen pull to the quantum foam's chaotic dance beneath spacetime, these 25 enigmatic regions aren't just cosmic oddities, they're frontiers where science itself stumbles. Each one defies expectations, shredding the rulebooks we've written for the universe. Black holes that erase information, voids that repel galaxies, singularities where time itself unravels. These aren't just puzzles waiting for solutions. They're glaring reminders of how much we don't know, how the cosmos reserves its deepest secrets for places we may never reach. Consider the implications. The Hercules-Corona Borealis Great Wall shouldn't exist under our current models, yet there it sprawls, mocking the cosmological principle. Dark flow tugs galaxies towards something beyond our observable horizon, hinting at forces or realms we can't fathom. Even the quantum void, empty by all appearances, seethes with particles blinking in and out of existence, as if reality itself is stitched together by uncertainty. These aren't just gaps in our knowledge, they're chasms, forcing us to question whether our theories are sturdy bridges or fragile rope lines swaying over the abyss. And yet, there's beauty in the mystery. Every anomaly, every paradox is an invitation to rethink, to explore, to marvel. The universe isn't just a static stage for human discovery. It's an active participant, hiding clues in the coldest voids and the hottest singularities, whispering riddles through the alignment of ancient light. These 25 regions remind us that science isn't about having all the answers. It's about the thrill of the chase, the humility of staring into the unknown and admitting, with equal parts frustration and awe, that we've barely scratched the surface. So where does that leave us? For all our telescopes and equations, we're still cosmic newcomers, piecing together fragments of a story far grander than we can comprehend. Maybe that's the most profound lesson of all. In a universe teeming with regions we can't explore, where the rules bend and break without warning, humanity's greatest achievement isn't solving the mysteries, it's daring to name them in the first place. Now it's your turn. Which of these enigmas keeps you up at night? Is it the Fermi bubbles towering over our galaxy like silent sentinels of some long-forgotten cataclysm? Or the axis of evil, that eerie alignment in the CMB that seems to whisper we're not as insignificant as we thought? Drop your thoughts in the comments, because the universe's greatest wonders aren't just out there. They're in the conversations they spark, the curiosity they ignite, and the collective wonder that binds us all under the same starry ceiling. After all, the next great cosmic revelation might begin with a single question, and who knows? Yours could be the one that changes everything.